A desert metropolis once flourished with gardens and fountains where none should exist. This was not magic, but a mastery of water achieved millennia before pumps or power grids. Our modern world faces a deepening crisis of scarcity and strain, yet the solutions may have been etched into the earth thousands of years ago. By the end of this exploration, you will possess a new lens for solving contemporary water challenges, drawn from civilizations that built for the ages. We will descend into subterranean rivers that defied deserts and examine aqueducts that moved mountains of water with only gravity's gentle pull. How did societies without steel or software create systems that outlast empires? The past holds a living textbook, its pages written in stone and soil, waiting to guide our future. What forgotten wisdom about living in balance with nature are we just beginning to remember? The heart of their success was not found in a blueprint, but in a belief. These ancient builders saw the land as a living partner and water as its most vital rhythm. They did not seek to command or reroute nature with sheer force, but to listen. By observing where rain gathered, how soil drank, and where underground rivers whispered close to the surface, they learned to place their structures within the existing flow of the world. This philosophy of harmony over domination created a profound resilience. A Roman aqueduct, for instance, did not blast through a mountain. It often chose a longer, gentler path that followed the land's contours, using gravity's patient pull. In the mountains of Peru, the Inca built extensive canals that mimicked the natural drainage patterns of the slopes, preventing erosion while nourishing terraced farms. Their goal was integration, a system that became part of the landscape itself. Compare this to many 20th century projects, which often relied on immense energy to bend rivers, pour concrete, and impose a rigid order upon dynamic systems. The ancient approach asked, how can we work with what is already here? This shift in perspective is the first and most vital lesson etched into these old stones. True sustainability is not about building a higher wall against the rising tide, but about learning the language of the water and designing a conversation that can last for generations. It is a quiet wisdom that challenges our modern instincts, urging us to see engineering not as an act of conquest, but as a form of careful cooperation. The quiet genius of their cooperation becomes visible in a single powerful principle. Ancient water systems were rarely vast, singular machines controlled from a distant center. Instead, they thrived on decentralization, a web of countless small solutions woven into the fabric of daily life. Think of the magnificent stepwells of India, known as bayolis. These were not just sources of water, they were community hubs carved deep into the earth. Each village or neighborhood maintained its own, a place where water gathering blended with social gathering, cooling retreats, and ceremonial practice. Far away in the rock-cut city of Petra, nearly every wealthy home had its own intricate system of channels and cisterns, capturing scarce rainwater from rooftops and courtyards for private use. This distributed model offered profound strengths. By collecting and storing water right where it was used, these societies eliminated the massive losses that occur when water travels miles through leaky canals or pipes. More importantly, it built resilience. If one stepwell silted up or a single household cistern cracked, the entire community did not go thirsty. The system had no single point of failure. This local management also cultivated a powerful sense of stewardship. When your family's survival depends on the cistern you maintain, you care for it with profound attention. The water was not an anonymous commodity from a far-off utility. It was a direct personal responsibility. This ancient insight challenges the logic of our modern megaprojects, the colossal dams and centralized treatment plants that represent monumental but often fragile achievements. The lesson is not to abandon large-scale infrastructure, but to weave it together with a revived network of the small and the local. Imagine a city where rooftop rainwater harvesting supplements municipal supply, where neighborhood-scale gardens are irrigated by recycled greywater from nearby homes. This creates a hybrid grid, one that is far more adaptable to drought or disruption, and crucially, one that reconnects people to the source of their most vital resource. It is a return to participatory care, updating an ancient, distributed wisdom for a world that needs resilience more than ever. Their philosophy of local care was powered by a force far simpler than any engine. Ancient water systems achieved the remarkable by harnessing the most fundamental law of the physical world, gravity. This was engineering at its most elegant, using the quiet, relentless pull of the earth to do all the work. The Roman aqueduct is the classic example, a monument not to power but to patience. Its builders were masters of the subtle slope, calculating gradients so precise that water would flow for dozens of miles, from a mountain spring to a bustling city, without a single pump or moving part. The water moved with a silent, constant grace, a testament to designing with nature's own momentum. Even more ingenious were the Persian Qanats, a technology so effective it sustained life in some of the world's most arid landscapes for over 3,000 years. Instead of fighting the desert, their builders listened to the hidden language of the water table. They would dig a mother well into the foothills of a mountain where groundwater was plentiful. Then, with astonishing skill, they would tunnel a gently sloping channel back toward the plains, sometimes for many miles, allowing gravity to guide the water underground, safe from evaporation, to the surface at their settlement. The system required no fuel, emitted nothing, and its gentle flow was self-regulating. This reliance on passive energy created a legacy of profound sustainability. It meant these structures were not just built, they were set in motion and could then operate for centuries with only basic maintenance. They were gifts that kept giving, generation after generation, because their power source was the planet itself. For us today, facing an energy-constrained future, this principle is a powerful call to rethink our assumptions. Modern water infrastructure is often an energy hog, relying on vast networks of electric pumps to push water uphill against gravity to treatment plants and towers. What if, like the Roman or Persian engineer, we started by asking a different question? Not how much energy can we apply to move this water, but how can we let the landscape do the work for us? This means designing with the land, not just on it. It could mean prioritizing gravity-fed municipal systems where topography allows, or using natural watershed contours to manage stormwater through green spaces instead of concrete pipes. It advocates for a site-specific intelligence, where the solution emerges from a deep understanding of the place itself, maximizing every natural advantage to reduce the carbon cost of every drop. It is a shift from active, high-energy intervention to thoughtful, low-energy orchestration, proving that sometimes the most advanced solution is also the most profoundly simple. Yet this elegant engineering was never merely about utility. Water was the lifeblood of a community in every sense, and the structures that carried it were designed to serve multiple layers of human need. A channel was not just a ditch for crops, it was a place of gathering, a source of spiritual reflection, and a work of public art. This principle of multifunctionality wove water systems directly into the cultural heart of society, making them indispensable and therefore cherished. High in the Andes, the Inca Asequias of Machu Picchu performed a symphony of roles. These stone-lined canals delivered precise amounts of water to ingeniously terraced fields, turning steep mountainsides into fertile gardens. But the water did not stop at agriculture. It was carefully channeled to ceremonial fountains and baths, where its flow was part of ritual and purification. The very path of the water mirrored sacred alignments, making the infrastructure itself a symbolic pathway connecting the people to the mountain deities and the cosmos. In Rome, the great aqueducts were monuments to civic life. They fed spectacular public fountains that were social hubs, supplied the vast bath complexes that were centers of hygiene and conversation, and even powered the flow that flushed the city's early sewers, improving public health on a massive scale. The aqueduct was not a hidden pipe. It was an arch testament to Roman ingenuity and generosity, a source of immense civic pride that everyone could see and benefit from daily. This holistic approach created what we might call added value, because the water system provided irrigation and ceremony and beauty and health. Its preservation became a cultural imperative. It was worth maintaining because it meant so much more than just hydration. It was part of the community's identity. We can revive this powerful idea today by moving beyond single-purpose gray infrastructure, the anonymous concrete pipes buried out of sight. The modern equivalent is called blue-green infrastructure. Imagine a city street where instead of a storm drain, there is a gently sloped, vegetated bioswale. When it rains, this beautiful green channel captures runoff, filters pollutants naturally through soil and plants, and recharges the groundwater, but its function does not end there. On a hot day, the plants release cooling moisture into the air, mitigating the urban heat island effect. The swale also creates a small habitat for birds and pollinators, adding a patch of nature to the urban landscape and simply being a pleasant, green space for people to pass by. One piece of infrastructure manages water, cools the air, supports biodiversity, and enhances human well-being all at once. This is the ancient wisdom of multifunctionality reborn, recognizing that the most resilient and beloved systems are those that nourish our lives in multiple, interconnected ways. They remind us that solving for water cannot be isolated from solving for community, for beauty, and for the health of the living world around us. But perhaps no ancient system better embodies this quiet, cooperative intelligence than one that flows unseen. To find it, you must travel to the heart of the Iranian plateau, a landscape of stark beauty and punishing aridity. Here, for over 3,000 years, a civilization thrived not by conquering the desert, but by conversing with it through a technology of breathtaking subtlety called the Qanat. This was not a dam or a canal, but something far more ingenious, a subterranean river engineered by hand. It began with a master shaft, dug with immense labor deep into the alluvial fan at the base of a mountain range, far down until its diggers struck the hidden water table. From this mother well, they did not pump the water up. Instead, they began the real work, carving a gently sloping tunnel backwards, horizontally, for miles across the desert plain, all the way to their settlement. The slope was the key, a gradient so precise, often just a fraction of a percent, that gravity alone would pull the water along this hidden highway, emerging at the surface as a reliable, year-round spring. Along the tunnel's entire length, a line of vertical access shafts was sunk from the surface, like a string of beads, providing air, removing spoil, and allowing generations of maintainers to descend and clear silt, keeping the life-giving vein open. The brilliance of this design was its profound harmony with a harsh environment. By moving the water underground, the Qanat eliminated the devastating evaporation that would have claimed it in an open desert canal. The water arrived cool and clean, filtered by its long journey through the earth, and where it emerged, it created an oasis, a micro-ecosystem of date palms, gardens, and community life that was literally fed from below. The Qanat was a lesson in sustainable extraction. It did not aggressively drain the aquifer, but rather tapped it with a gentle, constant pull that matched the natural recharge rate from the mountains, a balance that could be sustained for millennia. This low-tech, high-intelligence solution stands in stark contrast to our modern approach to groundwater, where powerful electric pumps can drain ancient aquifers in decades, leaving the land above to sink and salinate. The Qanat whispers a different possibility, one of patience and precise observation. It teaches us that the most powerful tool against desertification may not be a massive desalination plant, but a deeper understanding of the hidden hydrology already present, and the wisdom to design systems that work with its natural rhythm, not against it. In its dark, cool channel, we find a timeless blueprint for resilience, written not on paper, but in the silent flow of water through stone. While the Qanat mastered the hidden world below, another civilization perfected the art of moving water across the vast stage of the earth. The Roman aqueduct stands as a monument to a different kind of genius, one of ambition, precision, and logistical mastery. It was not enough for Rome to have water. It demanded a constant, lavish flow to supply its soaring population, its magnificent baths, and its very identity as the world's capital. To achieve this, Roman engineers became masters of the long-distance relationship with water, moving it across dozens, sometimes hundreds of miles of complex terrain. This was not a simple ditch. It was a carefully engineered river in a raised channel, a lifeline of masonry and mortar that had to maintain a perfect, gentle downhill slope from a distant mountain spring all the way to the city's heart. Their most critical tool was not a crane, but an instrument of sight called the chorobates, a long wooden frame with water-filled grooves that acted as a precise level. With this, they could calculate gradients so slight as 1 part drop for every 10,000 parts of forward travel. Achieving this over such distances, through forests, across valleys, and over hills, was a feat of surveying that rivals our modern satellite mapping in its ambition and accuracy. When the land itself posed an obstacle, Roman ingenuity provided an elegant toolkit of solutions. If a valley was too deep for a simple bridge, they might employ an inverted siphon, a sealed lead pipe that would carry the water down one side and back up the other, using the principles of pressure. For shallower depressions, they built the iconic arcades, those rows of towering stone arches that marched across the landscape, turning functional infrastructure into a symbol of imperial power and order. And when a hill stood in the way, they simply tunneled through it, carving subterranean passages with a relentless determination. But the brilliance of the system extended far beyond just getting the water to the city gates. The Romans understood that water quality and fair distribution were just as critical as supply. Before entering the city, water would often flow into large sedimentation tanks, where heavier particles of silt and sand would settle out, a primitive but effective form of filtration. Then at the terminus, the flow would arrive at a distribution castle or castellum. This was the hydraulic heart of the city, a central tank from which lead pipes branched out to different districts, to public fountains, to bathhouses, and to the homes of the privileged. The design of these outlets could be calibrated to ensure a measured, equitable allocation, an early form of municipal water management. This end-to-end thinking, from source to sedimentation to spout, represents a paradigm of project management and quality control that feels strikingly modern. It was not just about construction, but about the entire life cycle of the resource, planning for maintenance, purity, and public access. For our own era of massive pipelines, cross-continental grids, and sprawling urban water systems, the Roman model offers a timeless lesson. It reminds us that the greatest engineering challenges are not merely technical, but logistical and ethical. It emphasizes that meticulous planning, adaptive problem-solving, and a commitment to managing the resource responsibly at every step are what transform a grand project into a lasting legacy. Their aqueducts did not just carry water, they carried a philosophy of civic responsibility, flowing stone by stone, mile by mile into the future. Yet the most profound connection between water and community was not carried on arches, but carved downward into the earth itself. In the sun-baked plains of the Indian subcontinent, a civilization confronted the paradox of the monsoon, a season of torrential abundance followed by months of searing drought. Their solution was an architectural masterpiece in reverse, a structure that did not reach for the sky but embraced the ground. The stepwell, or baoli, was a cathedral built for water. It was not a simple hole with a bucket. Imagine a grand, inverted pyramid, its ornate walls lined with a symmetrical cascade of steps descending story after story, sometimes 10, 20, even 30 levels down, following the water table as it rose and fell with the seasons. This was architecture in dialogue with a living resource, its form a direct reflection of the aquifer's pulse. The design was a triumph of rainwater harvesting. The entire structure acted as a massive funnel. During the brief, intense monsoon rains, broad catchment areas at the surface would channel every precious drop into the central shaft, where it would percolate down, recharging the groundwater and raising the pool at the bottom. The steps ensured that no matter how low the water receded in the dry season, people could always descend to reach it, but the genius of the stepwell was that it served a purpose far greater than mere utility. Descending into its depths was a sensory journey. The temperature would drop dramatically, offering a cool, shaded refuge from the blistering heat above. The symmetrical geometry of the steps, often adorned with exquisite carvings of deities and mythological scenes, created a space of breathtaking beauty and profound tranquility. This transformed the chore of water collection into a social and spiritual event. Women gathering water would meet and talk, their voices echoing in the cavernous space. Travelers would find rest and respite. The stepwell became a community living room, a ceremonial site for festivals, and a silent sanctuary for meditation. It was infrastructure that nourished the body, the community, and the soul simultaneously. In its very design, it taught respect for the resource because to fetch water, you had to journey down to its level, witnessing its scarcity in the dry months and its abundance in the wet, fostering a deep, intuitive understanding of the cycle. This is the lesson etched into every stone step. Modern infrastructure often hides water away in sterile pipes and treatment plants, making it an invisible, abstract commodity. The stepwell challenges that. It asks, what if our water spaces were not hidden, but celebrated? What if a rainwater collection system was also a beautiful neighborhood park, a sunken garden with seating where the community gathers, and where the process of capture and infiltration is visible and educational? The baoli teaches us that when we make the management of our most vital resource a visible, beautiful, and social part of our lives, we build not just efficiency but a culture of care. It shows that the most sustainable systems are those we are personally, aesthetically, and communally invested in, structures so magnificent and meaningful that their preservation becomes an act of cultural pride for generations. But even the most ingenious physical system is only as strong as the human agreements that sustain it. High in the thin air of the Andes, where mountains touch the sky, the Inca and the cultures before them engineered something just as vital as their terraces and canals, a social technology for sharing water with profound fairness. This was the Asequias system, a network of community-owned irrigation channels governed by principles older than any written law. Here, water was never seen as a commodity to be bought or sold, but as a shared inheritance, a common good as essential as the air itself. Its distribution followed a clear, democratic logic, allocated not by wealth or power, but by demonstrable need and the size of one's land. A farmer with a larger field would receive a longer turn with the water, measured by the flow of sunlight across a stone or the draining of a simple bowl, while a family with a small garden plot would receive a shorter but guaranteed share. This ensured that every member of the community, from the most prominent to the most humble, had access to the lifeblood of their survival. The system was maintained through a reciprocal labor tradition known as aini, a concept meaning today for you, tomorrow for me. When the annual time came to clear the canals of silt and debris, every user would contribute their labor, knowing that this shared effort directly secured their own future harvest. Overseeing this delicate balance was not a distant bureaucrat, but a locally elected water steward, the mayordomo. This was a position of immense trust and respect, granted to someone with deep practical knowledge of the land and a reputation for integrity. The mayordomo's role was to walk the canals, mediate any disputes, and meticulously enforce the watering schedules, ensuring the principles of equity flowed as consistently as the water itself. This model of local, participatory governance created astonishingly resilient landscapes. At sites like the circular terraces of Moray, which acted as vast agricultural laboratories, the Asequias system delivered precise amounts of water to different microclimates, enabling the experimentation that gave the Inca their legendary diversity of crops. The system's strength lay in its transparency and mutual accountability. Everyone could see the rules, everyone benefited from their fair application, and everyone had a direct stake in the system's upkeep. This stands in stark contrast to modern water management, which often places control in the hands of far-off utilities, private corporations, or complex legal frameworks that can feel disconnected from the local reality. The Asequia tradition offers a powerful alternative vision, one where governance is rooted in place, knowledge, and collective responsibility. It argues that the most sustainable way to manage a scarce resource is to empower the community that depends on it to manage itself, guided by clear, agreed-upon rules and overseen by accountable local leaders. In a world facing increasing water conflict, this ancient Andean wisdom whispers a timely question. What if the path to water security is not through more control, but through more shared democratic care? While the Asequias channeled fairness through community law, another civilization achieved a different kind of balance, one that turned the very water they lived upon into their sustenance. The Aztec capital of Tenochtitlan was a marvel that defied logic, a glittering metropolis of canals and temples rising from the middle of a vast lake. With no surrounding farmland, the city faced an existential question. How do you feed a population of hundreds of thousands when you are literally surrounded by water? Their answer was an act of ecological alchemy, the Chinampa, often called a floating garden, though it was something far more stable and ingenious. These were not boats adrift, but artificial islands constructed with meticulous layering. Builders would stake out rectangular plots in the shallow lakebed using a framework of woven reeds and sturdy wooden posts. Into this frame, they piled layers of rich lake mud, sediment, and decaying aquatic vegetation, creating a new, fertile ground that was permanently anchored to the lake bottom. The result was a raised bed of exceptional richness, constantly fed by the capillary action of the water below. But the system's true genius was in its cyclical, waste-free operation. The canals that separated each Chinampa served as aquatic highways for canoes, but they were also liquid nutrient factories. Farmers would regularly dredge up the nutrient-dense muck from the canal bottoms and pile it onto their garden plots, a natural, continuous fertilization that kept the soil incredibly productive without any external inputs. Meanwhile, the canals themselves teemed with life. Fish and waterfowl found habitat among the sturdy root systems of the Chinampa plants, which in turn helped stabilize the banks. This created a symbiotic loop, a closed system where nothing was wasted. The Chinampas could yield up to 7 harvests a year, providing maize, beans, squash, flowers, and more for the immense urban population. This was not just agriculture, it was a deeply integrated agro-ecological system that blended food production, water management, transportation, and habitat creation into a single, harmonious whole. It represented a pinnacle of sustainable urban design, where the city and its life support system were one and the same. For our modern cities, often severed from their food sources by thousands of miles of supply chains, the Chinampa offers a radical vision of local resilience. It inspires the concept of productive urban wetlands and blue-green corridors, Imagine a city's stormwater retention pond redesigned not as a sterile basin, but as a constructed wetland that filters water through reeds and aquatic plants, while its edges are transformed into community garden plots using compost produced from local green waste. Or picture urban canals lined not with concrete, but with floating gardens that grow food, provide wildlife habitat, and cool the air. The lesson of Tenochtitlan is about closing the loop, turning urban waste streams, whether organic or water, into resources that fuel local abundance. It challenges us to see our cities not as separate from nature, but as ecosystems in their own right, capable of producing life and beauty from within. If we design with the same integrated wisdom that once made a lake blossom into a garden city. The sprawling stone temples of Angkor Wat are only the most visible part of a far grander achievement. This ancient metropolis was not just built on the land, it was a conscious reshaping of an entire watershed into a life support system of staggering ambition. At its heart lay a vast hydraulic grid, a network of colossal reservoirs called barrays, linked by a web of canals and moats that turned the unpredictable pulse of the monsoon into a steady, manageable rhythm. The largest of these reservoirs stretched over 5 miles long and nearly a mile wide, holding billions of gallons of water, an artificial inland sea carved from the earth. This was engineering on an imperial scale, designed to capture the torrential rains of the wet season, store them through the long, dry months, and release the water in a controlled manner to irrigate the rice paddies that fed a population likely exceeding 1 million people. The system transformed a landscape of seasonal extremes into one of predictable abundance, allowing the Khmer civilization to flourish for centuries. For a long time, we could only guess at the full extent of this network from the ground, seeing fragments of canals and the outlines of great barrays. But modern technology has peeled back the forest canopy to reveal the truth. Recent LiDAR mapping, a form of aerial laser scanning, has unveiled an astonishingly complex and extensive urban landscape beneath the jungle. The scans show a meticulously planned city, with canals acting as liquid streets, residential districts organized around smaller ponds and channels, and a hydraulic grid so sophisticated it suggests a deep, scientific understanding of hydrology and topography. This was not a haphazard collection of waterworks. It was the very circulatory system of a hydraulic metropolis, with water as its lifeblood and primary organizing principle. Yet within this story of triumph lies a poignant caution. Some researchers studying the LiDAR data and sediment cores from the old barrays have proposed a compelling and sobering theory. They suggest that the very success of the system may have led to its overextension. To feed a growing population, the Khmer engineers kept expanding their network, diverting more water, building more canals, and pushing the agricultural frontier further. This immense infrastructure required constant, labor-intensive maintenance to clear silt and repair breaches. Then, a period of intense climatic variability arrived, marked by severe droughts followed by catastrophic monsoons. The finely tuned system, stretched to its limits, may have become a liability. Canals designed for a certain flow could have been overwhelmed, reservoirs could have silted up faster than they could be cleaned, and the once reliable water distribution may have faltered. The theory posits that this combination of environmental stress and infrastructural strain could have undermined the agricultural base and social stability of the empire, contributing to Angkor's gradual decline and eventual retreat. This is not a story of engineering failure, but of a system that became a victim of its own success, pushing beyond the long-term carrying capacity of its environment. The lesson from Angkor is profound and deeply relevant. It warns us that even the most brilliant human designs are not immune to the forces of nature, especially a changing climate. It emphasizes that sustainability is not just about building a system, but about understanding its limits, its maintenance needs, and its resilience in the face of volatility. A water system must be designed not just for the climate of today, but with a buffer for the uncertainties of tomorrow. Angkor's legacy, therefore, is dual, a breathtaking testament to human ingenuity in harmonizing with a landscape, paired with a silent reminder that true harmony requires listening, adapting, and knowing when the land itself is saying enough. This ancient understanding of water's full cycle was not limited to grand reservoirs or farm fields. Deep in the foundations of a labyrinthine palace on Crete, another civilization was mastering a more intimate aspect of water management, one that protected life from an invisible threat. Within the Palace of Knossos, built by the Minoans over 4,000 years ago, archaeologists uncovered something that feels startlingly modern: a complex, integrated plumbing system. This was no simple well. The Minoans crafted tapered terracotta pipes that fit snugly together to supply fresh water throughout the sprawling complex, ensuring a reliable flow to rooms and courtyards. But their true innovation lay in what happened after the water was used. They engineered a sophisticated network of stone drains that carefully carried wastewater away, separating it from clean supplies. In some quarters, they even installed recognizable flushing toilets, with wooden seats and conduits that used rainwater to wash waste into these dedicated sewers. This was a civilization that, at the dawn of European history, had already grasped a critical public health principle that managing waste is as vital as managing supply. By prioritizing sanitation within their urban planning, the Minoans were actively guarding against the waterborne illnesses that would plague so many later cities. Their approach recognized that the water cycle does not end at the tap or the irrigation channel. It continues through use and must be returned safely to the environment. This holistic view is the bedrock of modern public health engineering. Today, we understand that sustainable water systems are complete loops. They must include not just the sourcing and distribution of clean water, but the effective treatment of wastewater to protect rivers, lakes, and coastal ecosystems from contamination. The Minoan pipes at Knossos whisper a timeless warning that a society's health is directly linked to its respect for the entire journey of water. It is a lesson written not in grand monuments, but in the humble, vital flow through clay and stone, reminding us that true sustainability is clean from start to finish. The silent lessons of Knossos traveled far, finding a spectacular echo in the rose-red cliffs of another desert kingdom. For the Nabateans of Petra, water was not just a resource, it was the very secret of their existence. In a landscape that receives barely a few inches of rain each year, and where that rain often arrives in violent, sudden flash floods, they performed a miracle of capture and control. They understood that to survive in such a place, you could not rely on distant rivers or deep wells alone. You had to become a master of the sky's rare outbursts, harvesting every single drop before the desert could steal it back. Their entire city was engineered as a colossal water catchment device, a testament to the principle that in the most challenging environments, the most advanced technology is often the simplest, a matter of paying exquisite attention. They sculpted the very rock faces to serve as watersheds, carving intricate channels and gutters into the cliff tops that would funnel rainwater from a vast area into a centralized system. But capturing the torrent was only the first step. Controlling its destructive power was the next. The Nabateans built a series of sophisticated dams and diversion walls at key points in the narrow canyons, or sikhs, leading into Petra. These structures were designed not to hold back water permanently, but to tame the flash flood, to slow its furious momentum, and redirect its flow into a managed network. The water was then guided through meticulously carved channels, some lining the canyon floors, others running along the rock walls, all leading to a hidden web of storage. They carved over 200 cisterns directly into the sandstone mountains, vast bell-shaped reservoirs that could hold millions of gallons, sealing them with a distinctive, pink waterproof plaster that prevented precious liquid from seeping back into the thirsty stone. This stored water became their lifeblood for the dry seasons, and then, with elegant simplicity, they used gravity. From the elevated cisterns, smaller channels and ceramic pipes distributed water down throughout the city, to public fountains, to wealthy homes with private baths, and to the lush gardens that must have seemed like visions of paradise in the arid expanse. Petra was not an oasis in spite of the desert. It was an oasis because of the desert's own sporadic bounty, harnessed with breathtaking precision. For modern cities in arid and drought-stricken regions, from the American Southwest to the Middle East and beyond, Petra is not just a ruin, it is a living manual. Its lesson is one of radical self-reliance and hyper-efficiency, emphasizing the critical need to maximize local water capture. It asks us why we let so much stormwater rush off paved cityscapes into overloaded drains, when it could be channeled into neighborhood-scale retention basins, underground aquifer recharge projects, or even the cisterns of individual homes. The Nabatean model inspires a shift from reliance on distant, strained water sources to creating a distributed network of harvest and storage, turning every building, every park, every street into a part of the solution. In their waterproof plaster and carved channels, we see a blueprint for thriving within limits, a powerful reminder that scarcity can be the mother of the most ingenious and enduring forms of invention. Far to the north of the desert kingdoms, in the sun-scorched basin of what is now Arizona, a different kind of water symphony was being composed. The Hohokam people looked upon the erratic flow of the Salt and Gila rivers and saw not an obstacle, but an opportunity waiting to be shaped. With tools of stone, wood, and bone, they undertook a project of staggering scale, etching a vast capillary-like network of canals across the desert floor. This was not a handful of ditches, but a managed watershed with primary channels stretching over 20 miles long and a total network exceeding 500 miles, all dug by hand and maintained through generations of communal labor. They transformed a floodplain into a fertile green lattice, supporting a population of tens of thousands with crops of maize, beans, squash, and cotton. Their genius lay in a profound understanding of the desert's own logic, a mastery of hydraulics achieved through patient observation. They engineered their canals with specific gradients to control the speed of the water, preventing erosion in some stretches and ensuring delivery to fields in others. They built clever headgates and diversion weirs from brush and rock to manage the flow from the river itself, especially during the volatile summer floods. But their most constant battle was against silt, the same fertile sediment that nourished their fields. As water slowed in the canals, this silt would settle, threatening to clog the very arteries of their civilization. The Hohokam developed a rigorous, scheduled maintenance ritual, a community-wide endeavor to dredge and clear the channels, season after season, year after year. This was not just manual labor, it was a social contract, a repeated act of collective commitment that literally kept their world alive. The system worked so well that it sustained their society for nearly 1,000 years, a testament to engineering and social organization in profound harmony. Yet, by around the middle of the 15th century, the great Hohokam villages were largely quiet. The canals began to fill for the last time. Research points not to a single cataclysm, but to a confluence of pressures. A prolonged period of drought would have lowered the rivers, making the elaborate system harder to feed. At the same time, major floods, possibly more intense due to a changing climate, could have breached canals and caused catastrophic siltation beyond the community's capacity to repair. Some scholars suggest these environmental stresses may have strained the social fabric itself, testing the cooperation required for the massive maintenance the system demanded. The intricate social cohesion that built and sustained the canals for centuries may have faced challenges it could not overcome. Their story is a powerful, sobering case study in the delicate balance between human ingenuity and environmental limits. It teaches that a water system is not just a set of physical channels, but a reflection of the society that builds and tends it. The Hohokam legacy offers profound insights for modern agriculture in river valleys worldwide, highlighting the need for systems that are not only cleverly designed but also socially sustainable, maintained by a community invested in their long-term survival. Their empty canals are a silent monument to a simple truth, that water management is at its heart an act of enduring partnership between people, their institutions, and the ever-changing land. The echoes of these ancient systems are no longer confined to history books or archaeological sites. They are being heard in the most practical of places, in communities facing a modern crisis of scarcity. From the sun-baked villages of Rajasthan, India, to the sprawling suburbs of Tucson, Arizona, a quiet revolution is underway, one that looks back to move forward. People are reviving the most fundamental of all water principles, capturing the rain where it falls. This is not about nostalgia, it is about survival, and it represents a powerful modern parallel to the wisdom we have been exploring. In Rajasthan, where aquifers have been plummeting after decades of overuse, villagers have resurrected a traditional structure called the johad. These are not massive concrete dams, but simple, crescent-shaped earthen embankments built across seasonal gullies. When the monsoon rains come, the johad slows the frantic runoff, allowing water to pool and, most importantly, to seep down into the ground, recharging the depleted water table. The results have been transformative, with dried-up wells refilling, rivers that had not flowed in years beginning to run again, and agricultural life returning to parched lands. This is ancient infiltration engineering, applied with community labor and local materials, proving its power once more. In Tucson, a city in the heart of the Sonoran Desert, the inspiration is drawn from many sources, including the cisterns of Petra and the catchment logic of the Nabateans. Here, modern adaptations are woven into the urban fabric. Homeowners install rooftop catchment systems, channeling rain from their roofs into above-ground barrels or large underground tanks, storing thousands of gallons for landscaping or even household use. On a municipal scale, cities are replacing impermeable asphalt with permeable paving in parking lots and sidewalks, allowing stormwater to soak directly into the earth rather than racing into storm drains. They are creating green infrastructure like bioswales, which are landscape depressions that capture runoff, filter pollutants through soil and plants, and direct water to recharge basins. These are all contemporary versions of the same ancient goal: to slow it, spread it, and sink it. What makes this revival so compelling is its hybrid nature. It blends deep traditional knowledge, the understanding of local watersheds and seasonal patterns passed down through generations, with the advantages of modern materials like durable plastics, advanced geotextiles, and precise gauges. It demonstrates that low-cost, decentralized solutions are not a step backward, but a critical complement to large-scale infrastructure. A neighborhood's collective rainwater harvesting cannot replace a city's reservoir, but it can dramatically reduce demand on that reservoir, especially for non-potable uses like irrigation. It builds resilience from the ground up, household by household, block by block. This movement is a living bridge between past and present, a testament that the most relevant solutions are sometimes the oldest ones, reimagined for a new era. It proves that the act of catching rain is timeless, a direct and democratic way for any community to reclaim its relationship with water and to write the next chapter of its own sustenance. This vision of catching rain finds its most ambitious modern expression in a movement reshaping entire urban landscapes. In cities across China, a radical new philosophy is taking root, one that directly channels the ancient wisdom of working with water's natural cycle. It is called the Sponge City Initiative, and its goal is to transform concrete jungles into living, breathing ecosystems that act like a sponge. Instead of viewing stormwater as a nuisance to be rushed away through pipes and drains as fast as possible, these cities are being redesigned to slow it down, soak it up, and put it to use. This is a profound shift from the gray infrastructure of the 20th century to a new paradigm of blue-green design. Imagine a city where rooftops are not barren tar and gravel, but thriving gardens that absorb rainfall, cool buildings, and provide habitat. Picture parking lots made of permeable pavement that allows water to seep through into the ground below, rather than pooling into oily puddles. Envision neighborhood parks that double as elegant detention basins, with gentle, grassy swales that fill with water during a downpour, filtering it naturally before releasing it slowly or allowing it to recharge the aquifer. This is the sponge city in action, a system that mimics the ancient, multifunctional approach of the stepwell or the Chinampa by weaving water management seamlessly into the fabric of urban life. The benefits ripple outward. By absorbing rainfall where it lands, these cities dramatically reduce the risk of devastating urban flooding, a growing threat in our era of more intense storms. They combat the urban heat island effect, as the evaporating water from green spaces provides natural cooling. They clean the water as it filters through soil and plants, removing pollutants before they reach rivers or groundwater. And crucially, they create local water reserves, capturing a resource that would have been wasted and using it to irrigate parks, flush toilets, or replenish dried-up waterways. This is not a rejection of modern engineering, but its evolution. It combines the ancient principle of infiltration, used for millennia in structures like the Johad, with 21st century materials science, data modeling, and urban planning. Sensors monitor soil moisture, smart systems manage water release, and new composite materials create durable, permeable surfaces. The sponge city shows how ancient hydrological wisdom, when scaled up with modern tools, can create climate-adaptive urban landscapes that are not just more resilient but more livable. It answers a question our ancestors would have understood intuitively: how can a city become a partner to the water cycle, rather than a barrier against it? The structures we have walked through were not just cleverly designed, they were built to last. Their endurance speaks to a mastery of materials that we are only beginning to fully understand. Consider the Roman concrete of their harbors and aqueducts, submerged in seawater for 2,000 years. Where modern concrete would crumble in decades from corrosion, these ancient blocks have grown stronger. For years, this seemed a mystery locked in time. Recent scientific detective work, however, has uncovered a secret ingredient with a remarkable property. The Romans mixed their concrete with a specific volcanic ash called pozzolana and chunks of quicklime. When seawater seeped into tiny cracks, it reacted with this lime, forming new crystalline minerals that actually filled the fissures from within. This was not a static material, but a dynamic one, capable of a primitive form of self-healing. It was a technology born from close observation of their local environment, using the reactive geology right under their feet to create a substance of legendary resilience. This same principle of local intelligence applied to waterproofing across the ancient world. The Nabateans of Petra perfected a distinctive pink plaster for their cisterns, a mix of lime and crushed ceramic that created an impermeable seal against the thirsty sandstone. In the stepwells of India, builders used a mortar made with local materials, including jaggery and fruit pulp, that bonded with the stone to resist constant water exposure. These were not recipes from a global supply chain, but hyper-local solutions developed through trial and observation that turned regional resources into enduring performance. The lesson for our own concrete-dominated world is profound. Modern Portland cement, the binder in most contemporary concrete, is responsible for a significant portion of global carbon emissions due to its energy-intensive production. What if we looked anew at the volcanic clays, industrial byproducts, or other reactive materials available in our own regions? Scientists are now doing exactly that, developing new generations of low-carbon, geopolymer cements inspired by Roman chemistry. The goal is to move beyond a one-size-fits-all material to a palette of region-specific solutions, creating durable, even self-healing infrastructure for water treatment plants, pipelines, and seawalls. This ancient material science teaches us that longevity is not just about brute strength, but about designing a dialogue between a structure and its environment. It suggests that the most sustainable concrete might not come from a distant factory, but from the chemistry of the local landscape itself, offering a path to building water systems that can maintain themselves for centuries, not just for decades. But a canal, no matter how brilliantly engineered, is just a ditch without people to tend it. The true foundation of any lasting water system is not found in stone or soil, but in the agreements between those who share it. Across cultures, ancient societies recognized that water's greatest challenge was not technical, but social, requiring governance as carefully crafted as their aqueducts. In the sun-drenched orchards of Valencia, Spain, a unique institution has met every Thursday for over 1,000 years. It is the Tribunal of the Waters, a court convened not in a building, but in the open air beside the city's cathedral door. Here, farmers who share water from the region's complex irrigation network bring their disputes before 8 democratically elected judges, fellow farmers who understand the land intimately. Cases are heard publicly, decisions are rendered verbally on the spot, and the rulings are binding, respected for their fairness and deep local knowledge. This is not a relic, but a living system of common law for a common resource, proving that legitimacy often comes from transparency and peer judgment. Far across the Atlantic, the Inca Empire orchestrated water management on a continental scale through a labor system called the mita. This was a form of rotational public service, where every household contributed a set amount of work each year to communal projects, including the maintenance of the vast Asequias networks and terraces. This was not forced labor in a punitive sense, but a recognized civic duty, a tax paid in sweat and time that directly sustained the community's lifeline. The system ensured that the massive, ongoing upkeep required by their hydraulic landscapes was distributed fairly and consistently, preventing the neglect that can doom any infrastructure. These models, from the formal court to the communal labor draft, reveal a universal truth. They are social technologies designed to solve the tragedy of the commons, the age-old dilemma where a shared resource can be depleted if everyone acts in their own immediate self-interest. The ancient answer was to create clear, culturally embedded institutions that defined rights, responsibilities, and consequences. They provided a forum for conflict resolution before disputes could turn destructive, and they organized the collective action necessary for perpetual maintenance. In our modern world, where water is increasingly a commodity, a source of geopolitical tension, and often managed by distant, opaque bureaucracies, these ancient frameworks offer a crucial mirror. They highlight the non-negotiable need for governance that is transparent, equitable, and participatory. When people have a voice in the rules and a stake in the outcome, when they see justice administered fairly and understand their role in upkeep, systems gain a resilience that concrete alone can never provide. The enduring lesson is that the most sophisticated pipe or pump is ultimately fragile without the human covenant to sustain it. A covenant built on shared need, mutual accountability, and the hard, honest work of living together. The silent resilience of these systems was forged in the crucible of a changing world. Ancient civilizations did not exist in a static bubble of perfect weather. They endured climatic shifts, prolonged droughts, and catastrophic floods, and their water engineering often emerged as a direct response to these very challenges. The Persian Qanat was not just a clever idea, it was a profound adaptation to extreme aridity, a way to coax life from a landscape that offered little. The vast barrays of Angkor were a monumental answer to the monsoon's volatility, an attempt to turn seasonal deluge into year-round security. By studying how these systems performed or sometimes failed under environmental stress, we gain more than historical trivia. We receive a masterclass in designing for climate resilience. These ancient engineers, without the concept of climate models, understood a fundamental truth: the climate is not a constant, it is a variable. Their most enduring works often built in a form of redundancy. A city with multiple qanats tapping different aquifers, or a community served by both a large reservoir and countless household cisterns, was far less vulnerable to a single point of failure. They planned for variability, designing channels wide enough to handle flash floods and storage deep enough to weather long droughts. Perhaps their most cautionary lesson, seen in the possible overextension of Angkor's network, is to avoid over-engineering for a single, stable climate condition. They show us the peril of optimizing a system so perfectly for yesterday's weather that it becomes brittle in the face of tomorrow's storms. For our own era of profound climatic uncertainty, this is a crucial strategy. It means designing water infrastructure not for the average, but for the extremes, for both the 100-year drought and the 1,000-year flood. It encourages modular, flexible systems that can be scaled up or adjusted as patterns change, rather than monolithic, rigid projects. It values diverse water sources, a mix of harvested rainwater, recycled greywater, and traditional supply, so that if one source falters, others can sustain the community. The past teaches us that resilience is not about building higher walls against the sea, but about cultivating a deeper adaptability within ourselves and our designs, learning to flow with change rather than fracture against it. The most powerful engineering is that which speaks not just to our needs but to our spirit. For countless ancient societies, water was never merely a physical resource. It was a sacred presence, a gift from the gods or the ancestors, and its careful management was a spiritual duty as much as a practical one. This profound reverence shaped the very form of their infrastructure, transforming functional structures into places of beauty, ritual, and communal meaning. In the temple complexes of South India, vast, geometrically perfect tanks called pushkarinis were not just reservoirs, they were integral to the sacred architecture. Pilgrims would perform ritual ablutions in their stepped waters before approaching the deity, physically and symbolically purifying themselves. The water itself was considered holy, a conduit to the divine. Far across the world, the Maya of Central America built elaborate steam baths and ceremonial pools within their ceremonial centers. These were not for leisure, but for spiritual renewal, places where rulers and priests would engage in rituals to commune with the underworld deities and ensure cosmic order, linking the flow of water directly to the stability of their world. Even in the more civic-minded Greek city-states, public fountain houses were often adorned with sculpture and dedicated to nymphs, turning the daily act of drawing water into an encounter with artistry and myth. This intrinsic spiritual value fostered a natural, deep-seated stewardship. When water is seen as sacred, its waste or pollution becomes a form of sacrilege. Its careful use becomes an act of respect, and its structures are maintained with a devotion that transcends mere utility. They are preserved because they mean something. This ancient perspective poses a vital question for our modern, utilitarian relationship with water. We have largely succeeded in making water invisible, buried in pipes, processed in distant plants, and delivered with the turn of a handle. In doing so, we have severed that visceral, emotional connection. The solution may lie in consciously reintegrating the aesthetic and spiritual dimension back into our built environment. This does not require building new temples, but rather designing with intention. Imagine a city where a rainwater harvesting system is also a stunning public sculpture, where the cleansing outflow from a treatment facility feeds into a serene, accessible wetland park that becomes a place for quiet reflection. Picture neighborhood bioswales designed not as anonymous ditches, but as beautiful, flowering rain gardens where children can learn about the water cycle by watching it in action. These are modern pushkarinis, spaces that invite us to see, hear, and appreciate water in our daily lives. By creating beautiful, accessible water features in our cities, we can begin to rebuild that lost sense of reverence and care. It moves us beyond viewing water as a commodity to recognizing it once again as the fundamental source of life, community well-being, and even wonder. When we encounter water with our senses and our spirit, we are far more likely to protect it with our hands and our hearts, completing a circle of respect that these ancient cultures understood was essential for survival. Even the most magnificent water temples eventually fell silent. For all their genius, the ancient engineers were not infallible, and their systems were not immune to collapse. These historical failures, often written in layers of silt or the quiet abandonment of a canal, hold warnings as vital as the blueprints for success. Take the grand reservoirs built by the Maya to sustain their cities through seasonal dry periods. Over generations, these open water bodies could become choked with sediment washing in from deforested hillsides, slowly reducing their capacity. More critically, in densely populated centers, these same reservoirs could become contaminated, a hazard to public health that may have undermined the very communities they were meant to support. This points to a universal vulnerability, the challenge of maintaining water quality alongside water quantity, a balance that requires constant vigilance. On a far larger scale, the sprawling hydraulic network of Angkor, as we glimpsed earlier, presents a profound case study. Its very scale, a triumph of imperial will, may have sown the seeds of its fragility. To feed a metropolis of over 1 million, the system was pushed to its hydrological limits, diverting and storing water on an unprecedented scale. When a period of intense climatic volatility arrived, characterized by severe droughts punctuated by catastrophic monsoon floods, this finely tuned machine may have been thrown into chaos. Canals designed for a certain flow could have been obliterated by floods they could not contain, while droughts would have lowered the reservoirs, concentrating pollutants and leaving fields parched. The immense labor required for maintenance might have become impossible to sustain, especially if social cohesion was strained by these very hardships. This was not a simple engineering failure, but a systemic one, where environmental shock met a society and infrastructure stretched too thin. These stories teach us that sustainability is not a one-time achievement, but a continuous, adaptive practice. They warn against the hubris of overexploitation, of designing for a single, stable climate that no longer exists. They highlight the non-negotiable need for adaptive management, the ability to monitor, maintain, and modify systems as conditions change. Most importantly, they remind us that water systems exist within a delicate web of social and environmental forces. A canal is only as strong as the community that tends it, and a reservoir is only as resilient as the watershed that feeds it. For modern engineers and planners, these ancient collapses provide a priceless risk assessment framework. They force us to ask uncomfortable questions of our own megaprojects. What are the long-term maintenance costs, not just in money, but in social commitment? How does the design account for climate extremes beyond historical averages? What happens if the population grows faster than the water supply? By studying where past systems broke, we learn to build in buffers, redundancy, and flexibility. We learn to listen for the subtle signals of strain, whether in dropping water tables, increasing salinity, or social conflict over access. The legacy of these failures is a gift of humility, a crucial check on our ambition, ensuring that our solutions are designed not just to function, but to endure through the unpredictable tests of time. The broken stones of past systems do not mark an end but a crossroads for our own. Our path forward is not a choice between ancient wisdom and modern technology, but a conscious fusion of the two, a synergy where each makes the other stronger. The goal is to take the decentralized, passive, and ecologically attuned principles of the past and amplify them with the precision tools of the present. Think of it as giving timeless intelligence a new set of eyes and ears. Consider the elegant logic of a Persian Qanat, a self-regulating underground river. Now place a network of simple, solar-powered moisture sensors along its tunnel and at the farm fields it feeds. These sensors would not control the water, but gently inform its keepers, providing real-time data on flow rates, aquifer levels, and soil saturation. A community app could then suggest optimal, equitable distribution schedules based on actual need, not just tradition, enhancing fairness while preserving the gravity-fed system's beautiful simplicity. Or envision the communal Asequias of the Andes, managed for centuries by the watchful mayordomo. Today, that steward could be aided by a basic artificial intelligence model, one trained on local weather patterns, crop types, and historical data. This digital assistant would not issue commands but offer predictive insights, whispering, "The next fortnight will be unusually dry. Consider extending watering times for the quinoa fields by 10%. It becomes a tool for foresight, allowing the community to make more informed decisions while the human values of equity and local knowledge remain firmly in charge. This fusion is not about automating care but augmenting it. We can use modern materials like durable, food-safe polymers for underground channels or advanced geotextiles to line rainwater catchment ponds to reduce maintenance and extend the lifespan of these systems. Drones can map watershed health, identifying erosion or pollution sources long before they become crises. The technology serves to deepen our connection to the water cycle, making its invisible processes visible and its subtle changes understandable. This approach rejects the either-or dilemma. It argues we do not have to abandon large-scale infrastructure, but we can weave it into a smarter, more responsive web that includes local harvesting, passive design, and community management. The resilience of the ancient model comes from its distributed, low-energy nature, the intelligence of the modern model from its capacity for monitoring and optimization. Together, they create a hybrid water grid that is both incredibly efficient and profoundly robust, capable of adapting to both daily fluctuations and long-term climatic shifts. It is a future where technology does not dominate nature, but listens to it more closely than ever before, allowing us to steward our most precious resource with a wisdom that is both ancient and utterly new. This fusion of old and new is already healing landscapes and communities. Across the globe, a quiet movement is proving that the most forward-looking solution is often to look back, to restore the water wisdom that was already written into the land. These are not museum projects, but active interventions where non-governmental organizations and governments are partnering with local communities to breathe life back into ancient systems, with remarkable results. High in the Peruvian Andes, communities are reviving a pre-Incan technology known as amunas. These are not canals for carrying water away, but for guiding it into the earth. Workers carefully restore stone-lined channels along mountain slopes, designed to capture seasonal rainwater and mist, slowing its flow and directing it to seep into specific zones of porous ground. This deliberate infiltration recharges the aquifers that feed natural springs further down the valley, which in turn supply water for drinking and irrigation months later. It is a brilliant, passive form of natural water banking, and its restoration is bringing dried-up springs back to life, securing water for villages that face an uncertain climate. On the other side of the world, in the arid mountains of Oman, a similar story unfolds with the restoration of the Aflaj. These are gravity-fed irrigation channels, cousins to the Persian Qanat, that have sustained Omani agriculture for thousands of years. Many had fallen into disrepair, silted up and cracked. Now, through community-led efforts, the channels are being cleared and relined. As the water flows again, so does opportunity. Date palm orchards that were withering are being revived, and a sense of cultural pride is rekindled alongside the harvests. The benefits of these restoration projects ripple outward in multiple, interconnected waves. The most immediate is increased water security, a buffer against drought that is engineered by the landscape itself. Then comes ecological revival, as restored springs and flowing channels create oases that support local biodiversity, from birds to insects to native plants. Crucially, these projects preserve intangible cultural heritage, protecting traditional knowledge and skills that are passed from elders to the youth, strengthening community identity and social cohesion. Perhaps the most powerful lesson is one of cost and effectiveness. Restoring an ancient Amuna or an Aflaj network is often far less expensive than constructing a new dam or drilling a field of deep, energy-intensive wells. It leverages the original, brilliant engineering that was designed specifically for that place, using local materials and labor. This makes it a culturally sensitive, ecologically intelligent strategy for sustainable development, one that empowers communities to be the stewards of their own renewal. These case studies offer a compelling alternative to the constant push for new, often disruptive mega projects. They ask us to see the old canals and channels not as ruins, but as dormant lifelines, waiting for the care and commitment to let the water sing through them once more. The enduring stone of an aqueduct or the deep cool of a stepwell carried a hidden economic logic within its design. These ancient systems were not just feats of engineering, they were masterclasses in long-term financial prudence. Their builders understood a fundamental truth, that the cheapest solution is not the one with the lowest price tag today, but the one that costs the least over a century. They achieved this by prioritizing three powerful principles: durability, locality, and passive operation. Structures were built from materials at hand: stone, earth, timber, and ceramic, minimizing transport and embodying the essence of local resource loops. More critically, they were engineered to function on gravity and seasonal cycles, requiring no fuel, no complex machinery, and very little ongoing energy input beyond human care. This combination meant that after the initial communal investment of labor, the system could operate for generations with only basic maintenance. The lifetime cost of a qanat that flows for 1,000 years, divided by the centuries of harvests it enables, approaches zero. This stands in stark contrast to the economic model of much modern infrastructure, which often emphasizes low initial capital cost but carries high, perpetual operational expenses. Think of a massive pumping station that requires constant electricity, expensive chemical treatments, and a specialized workforce to keep it running. Its financial burden is a recurring charge forever. The ancient model flips this equation. It asks for a higher upfront investment in thoughtful, durable design, but then rewards that investment with decades, even centuries, of low-cost, resilient service. This is the powerful economic argument being rediscovered by modern sustainable engineering. Green infrastructure, inspired by these ancient blueprints, follows the same impeccable logic. A city might invest more initially to install permeable pavement, green roofs, and a network of bioswales. This cost is real, but then the savings begin to accumulate quietly and powerfully. Energy bills plummet because less water needs to be pumped and treated. The need for expensive expansions to concrete storm drains and sewage treatment plants is reduced or delayed. Flood damage to property and roads, which costs municipalities millions in emergency repairs and recovery, is dramatically mitigated. The system pays for itself not through revenue but through costs avoided. It makes a compelling case that what is ecologically sound and socially beneficial is also financially intelligent over the long arc of time. This shifts sustainability from a moral or environmental imperative to a solid business strategy, one that values resilience and foresight as the ultimate forms of economic security. These principles of resilience must not remain the quiet secrets of history books. To truly embed them into our future, we need to begin where all lasting change takes root, in the minds of the next generation. Our educational systems hold the key to unlocking this lineage of wisdom, yet too often, the narrative of progress is presented as a straight line from primitive to modern. We teach students about massive 20th century dams and advanced water treatment plants, which are important, but we rarely introduce them to the Qanat, the Chinampa, or the Stepwell. This creates a profound gap in understanding. Imagine a curriculum where a lesson on hydrology includes the gravity-fed genius of Roman aqueducts. A unit on sustainable agriculture explores the closed-loop miracle of Aztec floating gardens. A class on civic engineering analyzes the social contracts that maintained the Hohokam canals for centuries. This is not about swapping modern knowledge for ancient, but about creating a rich comparative dialogue. It connects science, technology, engineering, and math, the STEM fields, directly with history, geography, and cultural studies, showing that innovation never happens in a vacuum. It is always a response to a specific place, a set of resources, and a community's values. When a student learns how the Nabateans survived in a desert by capturing every drop, they are not just memorizing a fact, they are absorbing a mindset of radical resourcefulness. They begin to see engineering not merely as applied physics, but as a deeply humanistic discipline, one that requires empathy for a landscape and collaboration with a community. This kind of systems thinking is perhaps the most vital skill we can foster. It allows a young person to look at a modern city and see not just buildings and pipes, but a metabolic system with inputs and outputs, vulnerabilities and opportunities. They might start asking different questions. Instead of just how can we get more water, they might ask how can we lose less? How can we design our homes and neighborhoods to be part of the water cycle? By grounding innovation in historical context, we free it from the tyranny of the new. We show that brilliant, sustainable solutions have existed across time and culture, and that this diversity of thought is a treasure trove for solving our own unique challenges. The goal is to inspire a new kind of problem solver, one who draws on a deep well of human ingenuity to design a world that works in harmony with its limits. This educational shift creates a powerful transmission of knowledge, not from teacher to student, but from ancestor to heir, building a bridge of understanding that can carry us toward a more thoughtful and enduring future. The legacy of these systems offers a powerful toolkit, not a single blueprint, for a world facing a water crisis of many faces. Its relevance spans continents and economies, proving that sustainable engineering is defined not by its technology level, but by its philosophy of harmony. In the rapidly developing communities of the Global South, where resources are often scarce but community bonds are strong, the most impactful solutions frequently echo the oldest models. Here, low-tech, decentralized systems managed by the people who depend on them can transform water security almost immediately. It might look like a village collectively building a network of improved rainwater catchment tanks, using modern, durable liners to prevent seepage, but following the ancient logic of capturing the sky's bounty where it falls. Or it could involve revitalizing traditional small-scale irrigation networks with simple, locally made gates for fair distribution, empowering communities to manage their own lifeline. These approaches prioritize immediate accessibility, democratic governance, and resilience built from the ground up, using resources and social structures already in place. Meanwhile, in the heavily paved cities of the industrialized North, The challenge is often one of overabundance and waste, where storm water is seen as a flood risk to be expelled. Here, the ancient wisdom manifests as a massive retrofit, a conscious undoing of the concrete seal. The solution is the integration of green infrastructure on a grand scale, turning spongy principles into municipal policy. This means mandating green roofs on new buildings to absorb rainfall and cool urban air. It involves systematically replacing acres of asphalt in parking lots with permeable pavements that let water sink into the earth. Cities can design parks that double as graceful detention basins, filling with water during a downpour and releasing it slowly, all while providing recreational space. This modern adaptation directly manages the stormwater that once caused destructive floods, reduces the oppressive urban heat island effect, and recharges local aquifers, all while making cities more livable. Though the tools may look different, a solar-powered sensor network in a European city and a hand-dug infiltration trench in an African village are guided by the same core insight. Both seek to work with nature's cycles, not against them. Both understand that water is best managed close to its source, and that the most resilient systems are often distributed, multifunctional, and deeply attuned to their specific place. This global relevance dismantles the outdated notion that advanced solutions must be complex, energy-intensive, or imported. It reveals a more profound truth, that the most adaptable toolkit for our planetary water challenge is one informed by millennia of human ingenuity, ready to be tailored to the unique needs of a bustling metropolis or a rural community alike. The question is no longer where to find the answers, but whether we possess the humility to recognize them in the quiet, enduring logic of the past. Yet unlocking this full potential demands a new kind of thinking in our own time, one that breaks down the very walls we have built around knowledge. The true story of a Qanat or a Chinampa is not owned by a single field of study. It lives in the intersection of many. To fully grasp why these systems lasted, we need more than an archaeologist's trowel uncovering its stones. We need a hydrologist to model its groundwater flow, a civil engineer to analyze the structural integrity of its tunnels, an ecologist to understand the microclimate it created, and a social scientist to decode the community agreements that maintained it for generations. Each discipline holds a piece of the puzzle, and only by fitting them together do we see the complete, brilliant picture. This is the urgent call for interdisciplinary collaboration. When experts from these isolated silos begin to talk, something remarkable happens. The engineer learns that the longevity of Roman concrete is not just a material science problem, but a question of local geology and reactive chemistry understood through trial and observation. The urban planner discovers that the success of the Asequias system was less about the slope of the canal and more about the cultural principle of Aini, the reciprocal labor that maintained it. This fusion of perspectives is what transforms a historical curiosity into a viable modern blueprint. It ensures that when we propose reviving an ancient water harvesting technique in a new city, the solution is not just technically sound on paper, but also culturally appropriate for the community and ecologically beneficial for the local watershed. It prevents the well-intentioned but flawed project, where a brilliant piece of ancient engineering is imported without understanding the social or environmental context that made it work in the first place. This collaborative model is already yielding fruit. Teams combining satellite archaeologists with soil scientists are identifying forgotten hydrological patterns beneath modern farms. Ethnobotanists working with civil engineers are rediscovering traditional plant-based water purification methods that could supplement modern treatment. This is not a rejection of specialization, but an elevation of it. It recognizes that our most complex challenges, like water security, cannot be solved by one kind of knowledge alone. They require us to build a common language, to sit at the same table and listen. The ancient builders did not see a separation between the technical, the environmental, and the social. Their work embodied all three. To honor their legacy and adapt it for our future, we must learn to think in the same interconnected way. The echoes from those ancient channels form a clear, guiding voice in our present moment. Our journey through these aqueducts, qanats, and stepwells reveals a profound and hopeful truth, that true sustainability is not a modern invention to be patented, but a timeless harmony waiting to be remembered. These civilizations, separated by oceans and millennia, all arrived at a similar wisdom by necessity and observation. They teach us that the most elegant and enduring solutions emerge from a deep conversation with nature, from thinking in closed loops and cycles, and from the unbreakable strength of communal care. Their legacy is far more than a collection of technical blueprints. It is a philosophical compass for our own age of crisis. It points us toward a form of engineering that seeks to heal landscapes rather than conquer them, to design systems that are partners in resilience, built to endure for generations rather than expire within a lifetime. This is the quiet revolution we are called to join, one that blends the intelligence of the past with the tools of the present. It invites us to look at our own rooftops and streets not as barriers to the water cycle, but as parts of it waiting to be reconnected. The compass is in our hands now, its needle calibrated by thousands of years of human ingenuity. If these lessons from the past resonate with you, and you believe they can help navigate our collective future, consider subscribing for more journeys into the mysteries of history that still speak to us today. We would love to hear your thoughts as well. Which of these ancient water systems, from the gravity-fed Roman aqueduct to the community-carved stepwell, inspires your vision for a more sustainable world?